Suppose that a block with a mass equal to 675 grams that we have labeled as M1 is on a frictionless 8-degree incline, and it is attached to a spring with a constant of 1.25 newtons per centimeter, and it's also attached by a pulley to a hanging mass that we've called M2, which is equal to 385 grams. How much is the spring stretched? And so we're assuming static conditions here. In other words, this is all in equilibrium. We're not making it oscillate, although we could, I guess, right? Maybe to clarify on the picture, I think, this thing is attached right here. So maybe imagine there's like super glue here, right? That's connecting the spring to the block, and it's not gonna let go or snap or anything like that. I think I'd like to start by drawing an FBD for mass M1. Maybe I need to consider M2 as well, but I think maybe if we're lucky that'll be a brief consideration. But I think for the mass M1, maybe it's easy to start with gravity, right? So that may represent the gravity force. There's going to be the pull of the string that is going over the pulley here. So that, I think the way things are drawn is going to be a kind of an 8-degree incline up from the horizontal, right? I may not draw that perfectly here. I'll do my best, but it's probably a little bit steeper than it should be. But anyway, there's that force. There probably be a normal force, right? But that's going to have to be at right angles to that force I just drew. At least I think it should be, because it's at right angles to the surface, and I'm kind of assuming this thread is parallel to the surface. That seems reasonable to do. And if the spring is really stretched, it would be pulling back on this system in the opposite direction of the string by some amount that might be a little bit less than the pull of the string, I think, because gravity is kind of helping keep the object in place there. I haven't labeled all these forces yet, and maybe I should. Let's see. I'm worried there's going to be too many, but anyway, FG, FN I think would make sense, right? This could be a tension force, so maybe I'll just put FT there for tension, and this is the spring force. Maybe I'll just put FS for that. I think that'll make sense, right? Sometimes if you get too many forces, people will just start saying F1, F2, F3, F4, F5, but because you might run out of letters in the alphabet otherwise, right? Whereas there's plenty of numbers, right? So anyways, for mass M2, I just want to quickly establish that it has a gravity force acting on it. It has a tension force acting upward. If it's in equilibrium, those two forces should balance. And I also think that this tension force here is the same magnitude as this tension force here. In other words, maybe I can just write in my picture here and say this tension force is going to be equal to this weight force here. But let me be clear about that, because we're talking about this weight force here in this picture is the weight of mass M2. So I'm going to put M2G. And if I'm correctly concluding from this picture that that is equal to the tension force, and then I can carry that over here, then I can say that this is equal to M2G. And that just saved me potentially a lot of work. I could have spent a lot of lines of math, I think, to draw that conclusion. But I think it's obvious enough from this picture. And so in that sense, I'd like to, whoops, I accidentally drew there. I'd like to focus my attention in terms of applying the concepts and those equations for force balance maybe to this more complicated free body diagram for mass M1 here. Now, looking at this, I see that kind of 3 out of the 4 forces are rotated away from what one might regard as like the standard direction that are implied by standard XY coordinate system. So maybe it would be neat to use a rotated coordinate system here. So that's something we've done earlier this semester in examples. And even though I didn't say anything when we looked at the key concepts for this chapter, there's no reason we can't still do that. So I'm just drawing in there kind of an XY. It can float anywhere. In physics, we don't really care so much where the origin is, right? When you're doing vectors, it doesn't matter as much. But that, as a guide, could let me write some equations then for either X or Y components. And I'm going to start by just looking at the sum of the X components of these forces. And on the key concepts page, I talked about, like, what should I do, like I equals 1 through 4? And if you've seen this notation in math class, usually in math class you're required to have that stuff. But as a physicist, the meaning of this to me is just I'm going to sum over four things in this picture here. And I understand that because I have this picture. My notation doesn't need to be perfect, is what I'm saying. Like in that sense, I don't need to follow all the rules that math class would tell me to follow with this kind of notation. It really just means add it all up, right? But we're adding up x components. Actually, I said there'd be four things, but maybe one of them won't be there, right? Because if I look at like what really are all these four forces, well, one of them, the normal force, is only pointing in the y direction. So the normal force, I think, is going to have no x component. And in that sense, I can maybe go through the other three forces and just write in what I think they are. And I think maybe two of them are obvious in the sense that there's I'm going to be explicit about minus signs here. I'm just going to make that choice and say that verbally, and hopefully that's okay. And I say minus Fs for the spring force plus that tension force. And I'm just going to use these labels here. But for the x component for gravity, that's one I might need to think about because it's not really pointing purely in the x or even in the negative x direction. It's kind of hanging a little bit there, right? But like in that sense, in relation to this coordinate system, right, the gravity force is like kind of pointing straight down right there. But there are components to it. Maybe I should focus on that picture a little bit more. Let me go to the side over here, because I'm kind of at a quandary as to what to continue with. Whoops, what am I drawing here? Let me start with my coordinate system. That was a great vertical line, but I didn't really need that. So I'm kind of redrawing this rotated coordinate system approximately, right? X, Y, and then I want plenty of space. This is what I think I was thinking about, is putting in my force of gravity there. And then, you know, the thing to recognize here, maybe I can put it somewhere in my picture, is we've rotated our coordinate system by 8 degrees, right? And if I were to look at the components, if I were to kind of draw the component vectors, kind of make it into like a component triangle, I like to call it, for this force of gravity, those components might look like those two arrows I just drew right there. And I think since I did a pretty careful picture, it seems kind of obvious to me that this angle right here would be that 8 degrees. And in that sense, if I'm looking at, this is the x component right here, that is opposite to that, right? So it might make sense that that would be equal to the magnitude of Fg. Let's see, opposite is sine, right? So I'm going to say sine of 8 degrees. I need to be a little bit careful though. I mean, I just analyzed this triangle here. I basically used SOHCAHTOA to figure this out. I mean, you could argue that sine is basically equal to the ratio of the x component to the magnitude of this force of gravity. But this points in a direction that is negative in relation to this coordinate system, so that's going to prompt me to throw in this minus sign here. Anyway, that lets me complete this part of this equation right here. Minus f sub g sine of 8 degrees. Might seem a little weird. I could have called this theta, I guess. It seems a little weird to be so like formal about everything and then throw in one number, but that's okay. It doesn't have to be perfect in physics as long as we get correct results, I guess, right? And as long as it's structured and followable, I think is important too. And you know, different people will make different choices at that. So if you do things slightly differently, that's okay. Anyways, let me kind of put into this. I think I might actually have enough here to be able to answer this question. That's at least what my intuition says. You might say, how do you know that, right? Well, I could be wrong, right? But part of the issue is like I don't have, normal force is kind of an unknown, but it's not in here anywhere, right? And what am I being asked for? I'm being asked for how much the spring is stretched, right? So if I look at the spring force, that's given by Hooke's law as k times x. Now I've chosen to be explicit about my minus sign, so each of these quantities should be regarded as positive. So I just put in a kx here. Sometimes some books will say Hooke's law is f sub s is equal to minus kx, and that could potentially lead to a pitfall, because if I plugged in minus kx and then cancel that with the sign that's already there, I'd actually get a positive thing here. But you know, these signs were explicitly related to this picture, so I really shouldn't do that. Okay, the tension force I've already related from this other picture over here is equal to m to g. And then this gravity force was for the picture for M1. So that one is equal to M1G. And I went ahead and already did all the component stuff I needed to do to get that sine of 8 degrees. And again, this is still equal to 0. And I made the claim that I think this is all I'm going to need to solve this. In other words, we have these different formulas for force balance, X component and Y component. So I could do Y component. Does that mean I'm always going to need to? Well, depends on what question is asked. So usually what I do is I start with one that I think might be useful. And if I decide that it's not going to be enough to answer the question, I go into the second one. But in this case, I think maybe it is, because if I look at the numbers that I'm given there, and I don't have a ton of space here, so maybe I'll just underline, right? I'm given that's that 1.25 newtons per centimeter. Might want to convert the centimeter to meters, I guess, later. But M2 is 385 grams, going to convert that to kilograms, right? M1 is the 675 grams, also will convert that to kilograms. G, of course, is G, so like maybe I can underline that as well and say, hey, that's something I know, right? And we already put in the 8 degrees, so we know that, right? And this is the thing I think I'm being asked for right here, because it says how much is the spring stretched, and in Hooke's law, that's what X represents. So that tells me that I have enough information to solve this. All I have to do is isolate X. And I think the thing I'm going to start with is, on this equation, is I'm going to add kx to both sides. Maybe actually make it convenient. Let me throw a little 0 over here. This may be a little, I don't know if that's a cheat or not, because we're supposed to relate to what's up there, but we said this whole thing's equal to 0, so I don't think it's cheating. So now I can add kx to both sides, right? And that means I'm just going to write kx over here and then rewrite everything else. Okay. And now if I want to solve for x, I should just divide both sides by k. So that gives me this somewhat largish but tractable expression. And at that point, I think I could, plug in numbers. And maybe if I had more space, I'd show all the conversions I'm going to do, but since I don't have a ton of space, I think I'm going to kind of do them on the fly. I'm a little nervous about the amount of space I actually have here. So you know what I'm going to do, I think? Let me move this equal sign down here. Okay. And now I think I've got more space to work with. That makes me less nervous. So, okay, let's see. M2 was equal to 385 grams, so I'm going to turn that into 0.385 kilograms. Times 9.81 meters per second squared. And sometimes I don't do units for the interest of space, but since I made all that space for myself, I'm kind of thinking maybe I can fit it in. Might be a bit of a stretch. But 9.81 meters per second squared. This is going to be, this is the one that's multiplied by that sine of 8 degrees. Okay, let me draw a line here. So something worth appreciating is this is probably a little bit more complicated than some of the other force problems we've done, although we've done a few complicated ones, but this was definitely up there, right? And one part of all this, it's good to follow all the analysis, be able to do the algebra, but when I write an expression like this, and especially when it has all the units in here, right, you need to be able to enter this into some kind of calculating, maybe I'll say thing, because it could be a handheld calculator. You could be using an app, I suppose, to do it. There are other online-based calculators you could do this with, so there's a lot of choices these days. But one of the issues with physics that we've often encountered is you have units, right? So you need to make sure not to enter those. And this one being kind of complicated looking fraction, probably if you enter it in line in most systems, you're going to want to put some parentheses before you divide by this number here. Anyways, that's probably something we all know, but as expressions get more complicated, one of the things that when I do this with people in class, I usually try to get everybody to do it right there, and then we all check our answers with each other. And that's kind of like why I'm checking the answer at the end here with the slide, is I want to encourage you to do that. And if you want to, you can pause the video and do your own calculation and see if you get an answer that agrees with mine. Let's see, I'm getting like 0.0228422 whatever, etc. And that's with all those unit conversions. We're calculating, that's presumably in meters. that's the other thing with complicated expressions like this. Tracking all the unit cancellations can also be a little bit difficult. But it looks like there's actually, when you look at this, kilogram meters per second squared, like that's a Newton, right? There's a Newton there in that term, divided by a Newton. But then there's this kind of sneaky 1 over m down here, came from the spring constant. And that, I think, is going to give us the meter that sort of survives all of this, that tells me that that 0.028, for some reason my pen went right for a second there, maybe because I was holding it wrong. All right, 0.0228, is that enough sig figs? I think we're working at about 3, yeah. Meters, okay? So that's the answer I got. Maybe it'd be nice to convert that into centimeters, right? In fact, that's what I did here on the answer in the slide.